Okay, in this example, we're told we have 1 kilogram of water contained in a piston cylinder assembly. So let's go ahead and sketch that out. We have our cylinder, here's our piston. We have some water in here. And we're told that the mass is 1 kilogram. We're told that the initial temperature of the water is 160 degrees Celsius. And the initial pressure is 150 kilopascals, absolute. Then we're told that it undergoes an isothermal compression process to a saturated liquid. So what that means is the process is isothermal, so that T2 will also be 160 degrees Celsius. And then we're told that the phase at state 2 is a saturated liquid. This will help us determine properties. It says for the process, the work done by the piston is minus 471.5 kilojoules. Actually, that's a misstatement in the problem. It should say the work done by the water is minus 471.5. So please make a note of that. So in this particular case, the water is our system of interest. So we'll just draw that like that. And then this is the work being done by the water. And there may be some heat transfer. That's in fact what we're going to try to find in part A. So we'll put a Q into there. So for this particular case, we're trying to find the heat transfer into the water. And then for part B, we want to find the change in entropy of the water. Okay, so to find the heat transfer into the water, we'll make use of the first law. And the reason I'm thinking the first law is because we're given information about the states. So we have some information about state 1. We have information about state 2. We should be able to find the internal energy for those states as well. And we're also given information about the work. In fact, let me write that down. The work done by the system is the minus 471.5 kilojoules. So with the internal energy and the work, we should be able to find the heat transfer using the first law. So let's write out the first law for that system. Change in total energy of the system is equal to the heat into minus the work done by the system. This should all be old hat for you. You've done this many times. The work done by, the change in total energy of the system will be change in the internal energy plus the change in kinetic energy plus the change in the potential energy of the system. We're going to neglect the changes in kinetic and potential energy because the piston cylinder arrangement, the water inside, these are not moving up and down or moving around to any appreciable degree. So we'll go ahead and neglect those. I'm going to go ahead and rearrange the first law to solve for the heat into the system. So that'll be delta U plus work done by the system. The change in internal energy will be the mass times the change in specific internal energy. So we'll just write that down. We know the mass. We know the work done by the system. So now it's a matter of just finding the specific internal energies for state 1 and state 2. So we can find those from property tables. I used the property tables out of the back of your textbook, the Moran and Shapiro textbook. So when I use that, so I'll just write here from property tables. We have U1 is equal to 2595.2 kilojoules per kilogram. And again, I used the values out of the back of your textbook. This was a superheated vapor phase for state 1. State 2, we're told, is a saturated liquid in the temperature, so we can look that up pretty easily. And again, out of the back of your book, I get 674.86 kilojoules per kilogram. That one, again, was a saturated liquid. We were given that information. If you use the Excel tables to find these properties, the values may be a little different, but the delta should be the same. Okay, so then if we go ahead and plug in our values for the mass, again, the mass value is given as 1 kilogram. The change in specific internal energy, we just calculated those, so it would be U2 minus U1. And the work done by the system were given as well in the problem statement. We can plug these values in, and what you'll get ultimately is the heat transfer into the system is minus 2390 kilojoules. So there's actually heat leaving our system rather than coming into it, since the value is negative. Okay, so that part's straightforward. You've done this kind of problem many times by this point. Let's go ahead and do the second part of the problem, part B, the change in entropy of the water. So this is just a simple matter of looking up the values for specific entropy in the tables. So again, from the property tables, you can look up the value for specific entropy for state 1. We're given the pressure and temperature for state 1. We know it's, from that pressure and temperature, we'll know it's a superheated vapor. We go to that particular table, and you'll find that S1. And again, I use the properties out of the back of your textbook, 7.4665 kilojoules per kilogram Kelvin. And then S2 is the saturated liquid value. Again, from the back of your textbook, I get 1.9427 kilojoules per kilogram Kelvin. Again, these come from the tables. And then if you want to find the change in the entropy, it's just a matter of multiplying the mass times the change in the specific entropy. So just it would be S2 minus S1. So we can go ahead and plug the numbers in for that. And what you'll get is delta S comes out to be negative 5.5238 kilojoules per Kelvin. You'll notice that the change in entropy is negative. And that's perfectly fine. There's no issue with having negative values for changes in entropy. You can have the change in entropy can be negative, it can be positive, it can be zero. What can't be negative is entropy production, the sigma term in the entropy equation. That cannot be negative. But delta S can be negative. If delta S is negative, what it means then is that the heat transfer must be out of the system. Recall from the entropy equation, let me just jot it down here. The entropy equation looks like this. So if delta S is going to be negative, then the delta Q must be negative because the sigma is either 0 or positive. And of course, the absolute temperature is always positive. So in order for delta S to be negative, the Q must be negative, and that's indeed what we found in part A of the problem. For the last part of the problem, this wasn't asked for, but I'll put it here anyway. Let's just draw a TS diagram of this process. So here's the temperature, here's the specific entropy. We'll draw the vapor dome since we're ending up at a saturated vapor state. Let me draw an isobar corresponding to state 1. Since state 1 is at 150 kilopascals, that's 1.5 bar, or you can keep it as 150 kilopascals. So let me draw the isobar for that. So this is P1 equals 150 kilopascals, absolute. Our initial temperature was 160 degrees Celsius, or state 1 is right here. Then our final state is also at 160 degrees Celsius, and we're at a saturated liquid phase. So that means our state 2 is over here. So our process, it's isothermal, so we're just moving horizontally from right to left. Here's our S1 value. You can see it's larger than S2 over here. Another interesting thing that we can just see graphically, we don't even have to look at the tables for this, but if you wanted to know how the pressure varies, the isobar for state 2 would look something like this. And so you'd see that the pressure for 2 should be greater than the pressure of 1. You can just see that graphically because we've moved upward on the we moved to a different isobar that's above the first isobar, and we know that that's, if you go in that direction, the pressure is